Okay, so good morning everyone. So what we will see today is the proof of Hastad switching lemma. So last time we saw how we can show that an AC0 circuit for parity will have a exponential size using the switching lemma, and today we will focus on how to prove this switching lemma. So one crucial difference in the statement of this lemma is that, so last time we kept the constant as gamma, which was roughly 4.16, but just to make the proof a little bit easier, we will show it for 16, but again with a little bit work it can actually be brought down to gamma as well. Okay, so let me just mention that as a note. So we keep the constant as 16 instead of gamma, which was I think 4.16, to keep the proof simpler. Okay. So how do we establish this proof? So the way we will establish this proof is we will count. So this kind of says that well, the number of bad restrictions. So restriction is bad if f restricted to that restriction cannot be represented as an SDNF. Okay. So we will count the number of such bad restrictions as a ratio of the total number of restrictions, and we will show that that ratio is less than this quantity. And the way we will count that number of, I mean the way we will count the number of bad restrictions is by giving an injective function. So we will take the number of set of all bad restrictions and we will give a injective function to another set which will be easier for us to count, and because it is a one to one function, so therefore I mean counting the size of the codomain will give us a upper bound on the size of the domain, and that will establish the proof for us. Okay. So let me just establish the notations and the framework of the proof. So let okay, so we have L equal to P of n over here already. So we will define Rk to be the set of all restrictions rho. So rho is a restriction that leaves k variables unfixed. Okay. And what is the size of Rk? So if you have a restriction which is keeping k variables unfixed, so in other words it is fixing n minus k variable, what is the number of, what is the total number of such restrictions? So we can choose first of all those k positions which are unfixed to be any of n choose k choices, and the remaining ones, the ones that we are fixing, either they go to 0 or 1. Okay, so there are two choices for them. So it is 2 to the power n minus k. Okay. Now we will define the set of bad restrictions. So let us call this set as B. Okay, so B is a subset of R L over here. So all restrictions rho such that rho belongs to R L. Okay, so just remember L is basically this the number of variables that we are unfixing in our lemma. Okay, so L is basically given by the lemma, it is a variable in the lemma, and F restricted to rho does not have a SDNF representation. Okay. So now what do we want to estimate? We want to estimate the size of or we want to estimate the quantity B by R L, right. So what we will show is, so this is the roadmap of the proof. So we will give a one-to-one map from B to R L minus S cross a set W, where cardinality of W is at most 40 to the power S. Okay. So this is essentially what we will be proving. So this is going to be the rest of today's lecture. And now once we have established this, okay, size of B is now bounded by the size of R L minus S times the size of W. So what is that? So once we have established this, then size of B by size of R to the power L is at most, what is the size of B? Size of B will be using this formula, it will be N choose L minus S times 2 to the power N minus L plus S divided by times 4t to the power S divided by N choose L 2 to the power N minus L, right. So these two cancel off, I get a 2 to the power S term over here. So and 2 to the power S into 4t to the power S gives me 8t to the power S. So this I can write as, so that is one simplification. The other thing that I get here is, how can I write this ratio, that is N choose L minus S divided by N choose L. So this will be what? L factorial into N minus L factorial divided by L minus S factorial times N minus L plus S factorial times 8t to the power S. Okay. How can I represent this? So this, note that we can write this as, okay, let me do it here, is equal to L minus S plus 1 up to L minus S plus S. So product of these terms. So there are S terms over here divided by N minus L up to N minus L plus S. So N minus L N minus L plus 1 up to N minus L plus S, right. Okay. So note that both in the numerator and denominator we have a product of S terms. So now I want to upper bound this. So I can upper bound this as follows. So this is S times the maximum term over here. So the maximum term over here is L. So I can write L over here, and so or L to the power s and divided by the smallest term at the bottom, which is n minus L plus 1 minus L n minus L plus 1. Okay. So, I will just keep it as an even smaller term, I will keep it as n minus L for the sake of simplicity. And what is L? So, L is equal to Pn for us. So, this becomes equal to Pn by n minus Pn dividing, I get P by 1 minus P whole to the power s 8 T of s. Now, I will use the fact that 1 minus P is greater than half. So, P is less than half, 1 minus P is greater than half. So, I get so this is bounded by 16 Pt whole to the power s. Okay. So, this is the calculation. So, now what we are left to show is this statement over here. Okay. So, now let us try to understand a few things about what f is. I mean, so f is given as a TCNF. What does that mean? So, because we have to estimate this probability, right? Yes. So, basically the total number of possibilities for row, okay, so or the number of rows which are bad divided by the total number of possibilities for row is this, right. So, if I choose a row randomly, the probability that it is bad is at most this. So, I am just estimating exactly that probability over here. It is all restrictions. So, R to the power L is set of all restrictions that leave L variables unfixed, and B is the number of bad restrictions as a subset. Okay. So, B is basically a subset of R to the power L. Main proof will now, so this is done. So, calculating this we have seen. So, the main proof now involves showing this. So, showing an injective function, first of all showing a function which maps this to this, and then showing it is 1 to 1, that is the main proof. And then of course, yeah, estimating the size of W. Okay. So, actually what we will do is we will give an encoding. So, given a restriction, a bad restriction row, okay, we will give a encoding of that. Okay. So, basically we will give a mapping of row into a string, and then we will show that that string is an element of R L minus S cross W, and to show that it is 1 to 1, we will show that given the image we can actually construct the pre-image uniquely. That shows that it is a 1 to 1 function. That is essentially what we will do. So, f is given as a TCNF. Okay. So, what we will first do is we will fix an ordering of the clauses and the variables within each clause. Okay. So, basically f is given to us as a TCNF, we will just look at a fixed ordering of the clauses, okay, so that we can refer to first clause, second clause and so on in a unique manner, and within each clause again we have a fixed ordering of the literals. Okay. Maybe it can be the alphabetical ordering of the whatever variables that are present in those literals. So, whatever it is, we just look at some fixed ordering. Next what we do is So, since rho is bad, that is it does not or f restricted to rho does not have a SDNF representation. Okay. What it means is that there is no clause that is identically 0. Okay. Because if I have a clause in this representation that is identically 0, then f is identically 0, right. And if f is identically 0, then well I can I mean forget about a restriction, I can represent f as as any DNF. I mean, so basically f is just a 0 function in that case. Okay. So, because f restricted to rho does not have a SDNF representation, therefore, it cannot be the identically 0 function. Because it cannot be the identically 0 function, therefore, there is no clause that is identically 0. Okay. There can be some clauses which are 1 and there are some clauses which are unfixed, that is which have some variables which determine whether it will be 0 or 1. Okay. Okay. Yeah, in f restricted to rho actually. Yeah. Okay. Now, since we cannot represent f restricted to rho as an S DNF, therefore, in the minimal DNF representation of f restricted to rho, okay, there exists a term whose size is how much. So, consider, so now look at f restricted to rho. Okay. By our choice of rho, we know that f restricted to rho does not have a SDNF representation. Okay. So, if I look at a minimal DNF representation of rho, what can we say about the terms in that representation? Can all the terms be bounded by size S? So, if in the minimal DNF representation, if all the terms are bounded by S, then f restricted to rho does have a SDNF representation, but by our choice that is not the case. So, therefore, there is a term that has greater than S variables. Okay. There has to be a term. Okay. So, now we consider another restriction. So, consider a restriction pi of these variables such that f restricted to rho pi is identically equal to 1. Okay. So, basically what we are saying is that now look at that term. Okay. So, there is this term which has greater than S many variables. Now, look at a fixing of those variables to some values. Okay, so if it is a literal in the positive form, then you set it to 1. If it is a literal in the negated form, you set it to 0. Okay, that is essentially the restriction pi. Now we have f restricted to rho, already some variables are restricted. In addition to it, if I also restrict the variables in this term, okay, then basically what do I get? It is a DNF representation. So if there is one term which evaluates to 1, the entire DNF evaluates to 1. So f restricted to rho followed by pi is identically equal to 1. Okay. So now we will be working with this rho and pi for the remainder. Okay. So is it clear what pi is exactly? Okay. So pi is basically the new restriction that we create whose size is greater than s. Okay, so size of pi is greater than s, that is very important, which is restricting these set of variables. Huh? All of those variables, because in f restricted to rho, all of those variables are unfixed. That is how we chose this thing. Na? So we considered f restricted to rho, it does not have a SDNF representation, which means there is a term in the minimal DNF representation whose size is greater than s. So all those variables are unfixed in that term. Now I am fixing pi, I am fixing those variables using pi. In that one term. Of course, it will be fixing the variables, I mean the corresponding variables in the other terms as well, but I am focusing on that one term. Okay. Now, identical equal to 1. It means that if I take the function f and if I fix the variables according to rho and pi, okay, the function is 1. It does not depend on the other variables any longer. The function is identical equal to 1. So this is identical equal to 1, this means this notation. So I will be using this actually quite a bit. So this is, let me write this, identically equal to 1, or if I write 0, it is identical equal to 0. Huh? What? Makes the function 1. We have selected pi in such a way, right? That is exactly how we selected pi, because we take a term in the DNF and we are fixing all those all the variables in that term. 1 or 0, I mean the variables depend. So if it's, let's say, if that term, let's say, looks like something like x1, x3 bar, x4, then I will set x1 to 1, x3 to 0, x4 to 1. So therefore that term becomes 1. Now if in a DNF representation even one term is 1, the entire function is 1. Okay. Therefore it is identically equal to 1. Okay. Now because this is setting this, so f restricted to rho pi is setting this to 1, if I look at this restriction in the CNF representation, what does it say about the CNF representation? So in the T CNF representation, f restricted to rho pi or every clause in f restricted to rho pi is 1, okay, because it is a CNF representation. Therefore, for the CNF to be 1, each and every clause must be 1. So therefore, this restriction is ensuring that each and every clause is 1. Okay. Now we will once again do a small construction, or not a construction, but we will constructively will give a way to come up with a clause. Okay. So, let C1 be the first clause in F restricted to rho that is not identically 1. Okay. Let pi 1 subset of pi be the variables in how do I write this, that are restricted by pi, and let us say that size of pi 1 is some d1. Okay. Now, there exists a unique setting of the variables in pi 1, okay, let us call it say pi 1 bar, such that C1 is not identically 1 with respect to F restricted to rho pi 1 bar. Okay. So, let us try to understand what we are saying here. So, maybe it might be better to keep a picture. Okay. So, this is the most crucial part of the proof. So, let us try to understand this. Okay. So, we have these clauses. So, let us say we have 8 clauses in F. Now, initially let us assume that none of the clauses are possibly 1. So, this is my F. Now, if I look at F restricted to rho, well, some of the clauses becomes 1 over here. Okay. Let us say that this guy becomes 1, this guy becomes 1, this is unfixed, maybe this is also unfixed, 1, unfixed, 1, unfixed. And we know that in F restricted to rho, no clause is identically 0, because if any clause is 0, then the entire thing becomes 0, and therefore, it will always have a SDNF representation. So, it is either 1 and some are unfixed. Now, what we know about F restricted to rho pi? So, in F restricted to rho pi, everything is 1 by our construction, right. Now, what is pi 1? So, look at the first clause. So, because in F restricted to rho, there has to be some clause that is not 1, okay, because it does not have a SDNF representation. Look at the first clause. Okay. So, C1 here is essentially this clause. Okay. The first clause that is not identically 1. Okay. And now, pi 1 is the subset of pi. So, by subset, so this notation is actually little overloaded. So, by subset what I mean is that look at the variables that are restricted by pi and look at the subset of those variables which belong to the clause C1. Okay, essentially that is what it means. So, now if I look at the set of variables that are here, so what can I say about f restricted to rho pi 1? What can I say? Everything that was 1 before has to be 1 because they are anyway I mean the same restriction applies. What can I say about C1? Huh? C1 becomes 1 just by the again the definition of pi 1. Okay. And later on again maybe this is question mark, whatever was 1 anyway remains 1. This one maybe some other clause might get also set to 1, let us say this also gets set to 1 and this remains question mark. Okay. So, this is our pi 1 and we are let us say the size of pi 1 is some d1. Now, what is pi 1 bar? Okay. Pi 1 bar is, so look at these d1 variables. Okay. Now, because it is a CNF representation, so I have an OR of literals, there is a unique setting of those d1 variables, okay, such that that clause does not evaluate to 1. How can I do it? I mean basically I have those variables, right. So, so now in a, if I have an OR of literals, even if one literal is set to 1, the entire clause becomes 1. Okay. So, I have to ensure that each of those those d1 variables are 0. Okay. So, if I have a variable in the positive form, then I will set that to 0. If I have a variable in the negated form, then I will set that variable to 1. Okay. So, each of those variables or each of those literals remains 0, each of those d1 literals. That is exactly what we are doing in this construction. Now, if I look at f restricted to rho pi 1 bar, what can I say? What about the clauses before C1? Huh? Those remain 1 because anyway rho was restricting them to 1. Okay. So, I already have rho, they do not change. What about C1? Huh? Well, it does not become 0, it becomes unrestricted now. No, we are not fixing everything. See, that is the thing. Okay, so let's look at an example. Okay, so this is a very good point. So suppose my C1 looked like this something. Okay, so let's say it had. Okay, let's take some examples. So x1 or x2 bar or x4 bar or x5. Suppose. Okay. Now, suppose x1 belonged to rho. So, rho had already fixed x1. Okay. So, after when I look at C1 restricted to rho and let us say that x1 was getting fixed to 0. I mean of course, it has to get fixed to 0 because it was not. So, C1 restricted to rho was looking something like this 0 or, so I can just erase the, I do not need to write this. So, x2 bar or x4 bar or x5. Now, my pi 1 can just fix any one of these literals, it need not fix all the remaining literals, right. So, pi 1, let us suppose in pi 1 I had, it contains the restriction say x2 equal to 0. So, if I set x2 equal to 0, then this clause gets evaluated to 1. Suppose pi 1 does not even look at, sorry, this was x4, pi 1 does not even look at what x4 and what, or pi 1 does not set x4 and x5, okay. Even then this clause gets set to 1, okay. So, now with this setting C1 restricted to rho pi 1 is identically 1, right. Now, what I am doing is I am setting only the variable x2 in pi 1 bar. Okay. So, now what I do is that in pi 1 bar I will have x2. So, because this is in the negated form, I will keep it as 1. So, yeah, I will have this restriction, and now what does this become? C1. So, as a result, C1 restricted to rho pi 1 bar is now equal to, this becomes 0. So, I have x4 bar or x5. So, it is not necessary that it will become 0, it just becomes question mark. Pi 1 bar is what? Say it again.
Pi 1, whatever variables we have restricted, we just manipulate the variables in such a way that the restriction just goes away. We make it 0 or 1, such like.
Exactly. So, we manipulate it, but it is not necessarily the complement of pi, because I will give you another example. Suppose in pi 1, say x2 was being set to 0, and suppose x5 was also set to 0 in pi 1. See, setting x5 to 0 is not helping this clause becoming 1, right. It is x2 0 which is making this 1. So, suppose I have pi 1 where x2 is equal to 0, and so this is a good example, and x5 is equal to 0. Now, what is pi 1 bar now? In pi 1 bar, I have to give a setting to x2 and I have to give a setting to x5. Huh? No, x5 will have to be 0, because if I set x5 to 1, then this clause becomes 1. So, look at the definition. So, there is a unique setting of the variables of these D1 variables such that the clause is not identically 1. So, if I make x5 as 1, the clause becomes identically 1. Okay. So, in pi 1 bar, this is also equal to 0. So, it is not necessary that it is just a complement of pi 1. Okay. It is setting those variables appropriately.
If the pi 1 is restricting all the variables x2, x4 and x5,
yeah,
then the pi 1 bar will also have to restrict all the variables.
It will restrict all the variables, yes, but
then it will have to get 0.
no. Well, yeah, in that case, yeah, then it will have to get 0. So, it should not be identically 1. It can get 0, yeah. But see, the point is, no, it will. Huh? Then the entire thing is 0, that is true. Yes. It is this. Huh?
What does it mean to say that restricted by pi? So here in this clause x1, x2, x4 and x5 are restricted by pi.
No, in this clause only x4, x2 and x5 are restricted by pi, not x4. Right.
No, pi is a separate, like here you are considering pi 1.
So, pi 1 is a subset of pi restricted to this clause. Okay. So, in pi x4 was not getting restricted, only x2 and x5 were getting restricted. So, I just picked those. Okay. And the key thing is that now once I have pi 1 bar is a unique assignment. There is only a unique assignment, because in pi 1 bar each of those literals must be 0. So, there is a unique way of fixing each of those variables so that that literal goes to 0. Okay. So, this thing is very important over here. Okay. And this is actually the key idea. Okay. Now, why is this the key idea? This comes from the next statement. Now, given rho pi 1 bar, we can now uniquely identify C1. Okay. So, essentially if I am given row pi 1, note that by our construction, so these remaining things can be anything, but by our construction C1 is once again the first clause that is unrestricted with respect to this restriction row pi 1. Okay. So, if I am given this restriction, then I can uniquely identify what my clause C1 was. Okay. And we will see later on that, and with some more info we can get pi 1 and pi 1 bar as well. So, what that information is we will see later on, but the key thing is that to find out C1, if we are given row pi 1 bar, we can uniquely identify C1. Okay. Now, what is the set, I mean what is the size of this restriction, or from which set do we pick this restriction? So, how many variables are being fixed over here? So, row fixes how many variables? L variables. How many variables pi 1 bar is fixing? D1 variables. Okay. So, the number of variables that are unfixed is L minus D1, right. So, row pi 1 bar, so note row pi 1 bar belongs to R L minus D1. So, in row basically L variables were unfixed, now I have fixed another extra D1 variables. So, row pi 1 bar belongs to RL minus D1. Okay. So, now yeah, we continue in this manner. So, we define C2. Okay. So, C2 is defined to be the clause or the first clause that is unfixed by just read this. Not fixed to 1 by row pi 1. Okay. Pi 2 is basically the remaining set of variables, that is it is a restriction of pi minus pi 1, okay, to C2, and let us say that D2 is the size of pi 2. Similarly, pi 2 bar is the unique setting of variables in C2 such that C2 is not identical equal to 1. Okay. So, we just continue in this manner. So, we have row pi 1. Okay. So, in row pi 1 C1 got set to 1. Now look at the first clause that is not set to 1 by rho pi 1. Okay, so it is only setting some d1 variable, so there will be some other clause that is not being set to 1. Look at that clause. Look at the remaining set of variables in that clause. Okay, so from pi, remove the variables of pi 1. Okay, and look at the variables that are present in C2. Okay, so this will be our C2 in this case, so rho pi 1. So this is our C2. Okay. So look at the remaining set of variables. Yeah. So look at the remaining set of variables over here. Okay. Now pi 2 bar once again is the unique setting of those variables such that C2 is not 1. Okay. And we keep on continuing this. Okay. So how long do we continue? So we will continue unless and until we get S variables. Okay. So in general, let me write this, Ci is equal to first clause, that is not fixed to 1 by rho pi 1, pi 2 up to pi I minus 1. Now pi I will be the restriction of pi minus pi 1, pi 2 up to pi I minus 1. So remove all these variables from pi and look at what remaining variables belong to this clause. Okay. And now pi I bar is the unique setting of the variables sorry, this one is not C2, this is pi 2. So unique setting of the variables in pi 2 such that C2 is not 1. Okay, so unique setting of the variables in pi I such that Ci is not identically 1. Okay. So we continue or let me just write this as we end this process once we have restricted exactly S variables. Okay. So we get pi 1, pi 2 up to pi k, and correspondingly pi 1 bar up to pi k bar. Okay. So what are we saying? So well, in first stage we have restricted d1 variables, then we restrict d2 variable. Okay. In the ith stage, well, I haven't written it over here, but I can write it over here. Di is basically the size of pi I, right? How did I write this? Yeah. di is equal to size of pi I. So, we continue till we reach a point where the sum of these di's is exactly equal to s. Now, note that what do I mean by exactly equal to s? Now, look at this last restriction. So, in that last restriction, it is not necessarily that I will be restricting all the variables. So, basically I would have found a clause Ck which is unrestricted. So, in Ck I will only pick that many variables which would give me a total of s fixed variables. Okay. So, note in the last step only a subset of the variables in of pi might be restricted in Ck, but that is okay for us, it does not matter. Even restricting a subset will keep that as unrestricted. Okay. So, now
So, in this subset in the last clause, will we select the
first, yeah, first few variables such that it becomes exactly s. And now I look.
It won't matter if like none of the like the restriction just restricted to these variables, if it does not set it to 1.
It, well, with setting so restricting it to those variables will not set f
F row
pi 2 up to pi k to 1, it will not set that clause to 1, okay. But that actually does not matter to us. What matters to us is that even f restricted to row pi 1 bar, pi 2 bar up to pi k bar will not set that clause to 1. That will be true, and that is actually what matters for us. Okay. That is what we will be using next. Yeah, actually I think I can erase the statement of the lemma as well, because we are just proving a slightly different thing. Okay. So, let pi star bar be equal to pi 1 bar, pi 2 bar up to pi k bar, and rho star is equal to rho pi star bar. Okay. We will also define two strings. So, remember that what I said is that firstly we will be identifying these clauses. So, we saw how we can identify C1. Okay. Now, note that if we are given row pi 1 bar, pi 2 bar, okay, then and along with it I am also given, let us say, what pi 1 bar is. Okay. So, I fix according to, or sorry, let us say I am given pi 1 and I am given row pi 1 followed by pi 2 bar, then I can uniquely identify C2, right, because C2 will be the first clause which is not set to 1 by row pi 1 pi 2 bar, because pi 1 is already setting C1 to 1, and by our construction that is the first thing. So, that will give us. Now, the question is that we can identify these clauses in this manner, but how do I get pi 1 pi 2 bar? Okay. So, I said that with some little bit of more information I can actually get what these restrictions are as well. That is what I will define next. Okay. So, define for all I belonging to 1 to k, okay, ai belonging to 0 1 to the power t. Okay. What was t? So, t was the, so we took a TCNF. Okay. So, t was the maximum size of a clause. Okay. So, essentially what I will do is, so a I of j, so the jth bit, so ai is basically a t bit string. So, the jth bit of ai will be equal to 1 if the jth variable in C I is set by pi I and it is equal to 0 otherwise. So, if the jth variable is one of those di variables. Okay. So, note that in Ci there are di variables which are fixed by pi I, right. So, if the jth variable is one of those, so that fixing can either be either fixing to 0 or fixing to 1, then I will set ai j to 1, otherwise I set it to 0. So, essentially what ai helps us in figuring out is which are the variables in a clause that are being set by pi I, okay. And I have k of them. So, I know all, I mean I know it for all pi 1 up to pi k. I will also define another string define b belonging to 0 1 to the power s as, so b of I is equal to the have I written it? Okay, equal to the value to which the ith variable is set to by pi 1 up to pi k. Okay. Yeah. So, note that we are fixing a total of s variables. Okay. So, we had chosen pi 1 up to pi k such that s, a total of s many variables were getting fixed. So, bi is basically the value to which these restrictions are fixing those s variables. Okay. So, the exact value. So, if let us say pi and of course, note that all these pi's are distinct by the construction, they do not overlap, all of them are distinct. So, if some pi t some pi k is setting, or pi not k, pi maybe pi g or something, if pi g is setting some variable to 0, then b of I of that variable bi will be 0 and otherwise it is 1. Okay. So, now the last, or not the last, but the second last claim is why is this an injunction. Okay. And lastly, we will talk about the size. So, claim given rho star these ai's I going from 1 to k and b, we can uniquely construct rho. So, if I am given this rho star, that is rho pi bar or pi star bar, and these strings ai's and b, then I can uniquely construct my function rho, and not just rho, we will show that we can actually get all of these pi i's and pi I bars as well from this. So, this proof is actually easy, it follows by our construction. So, once again, first we will get C1. What is C1? Okay. So, C1 is the first clause not identically 1 with respect to rho star or let me use the notation actually instead of writing this manner. The first clause in f restricted to rho star that is not identically 1 is C1. So, we get what our C1 is. Now, we use A1 and B to identify pi 1 and pi 1 bar. How do we get it? So, I have C1, I look at A1 first. So, A1 will tell me exactly which are the variables which were set by pi 1, I know what those variables are. B will tell me what are those values that they were set to. Okay. So, it now tells me what pi 1 is. Now, once I know pi 1, I have my clause C1, I can look at the clause and I can look at my values of pi 1 and I can get pi 1 bar, because pi 1 bar is a unique setting of those variables such that that clause does not become 1. Okay. So, I have this. So, I have gotten pi 1, I have gotten pi 1 bar and I have gotten C1. Now, next I again go in a iterative manner. So, let rho 1 be equal to rho star minus. So, in rho star what do I have? In rho star I have rho followed by pi 1 bar, pi 2 bar up to pi k bar. So, I will remove pi 1 bar from rho star. Okay. Now, those variables which were being restricted by whatever pi 1 or pi, in this case pi 1 bar, I remove them from rho star. Okay. And I will add the restriction pi 1. Now, what does this achieve? This is exactly what I said earlier. What this achieves is that this makes C1 equal to 1, because pi 1 makes C1 equal to 1. So, now what can I say about rho 1? What can I say about this? Exactly. The first clause here that is not identically 1 is C2 now by the very construction. Okay. Okay. So, first clause here not identically 1 is C2. Okay. Once again use A2 and B to get pi 2 and pi 2 bar. Now, continuing in this manner, we get pi 1 up to pi k and pi 1 bar up to pi k bar. Okay. So, now here you can see why only getting a subset of the variables of the last clause was good enough for us, because what we only want is that that clause should remain unrestricted. That is the only property that we are using here. It is not necessary that each of those variables are being set to 1 by pi k. that is all, okay, because after that we do not proceed anymore. So, this proves that it is a injective function. So, given rho star AIB, I can uniquely okay. So, I have gotten this. So, now I have all this. So, how do I get rho? So, what is rho? So, I know all of this, I know rho star. So, therefore, we can obtain rho. Okay. Just remove these restrictions pi 1 bar up to pi k bar from rho star, that is all. So, this completes the proof of this claim. Okay. So, now we have established that it is a one-to-one function. What is left to prove? That the size of this string or this string actually comes from a set of size whatever r, I mean whatever was it, RL to the r to the power L minus s times w. So, that r to the power L minus s is clear because so how many variables are restricted in rho star? So, already I have L variables restricted by rho and pi bar pi star bar is restricting another s variables. Okay. So, rho star belongs to r to the power L minus s. Okay. So, that many variables remain free. So, that part is done. So, now we have to show that and what is the size of the string B? So, B well B belongs to 0 1 to the power s. So, B comes from a set of size 2 to the power s. So, we have R L minus s, we have 2 to the power s. So, now the only thing that is left to show is that I going from 1 to k comes from a set of size how much? How much do we need? So, W was 4t to the power s, I already have a 2 power s. So, what remains is 2t to the power s. Okay. So, this I will so there is just 2 observations which will actually give this. The first observation, what is the structure of these AIs? Okay. So, note that each AI comes, so each AI is basically a binary string of length t and each AI has at least one 1, right, because at least one variable. So, in each of these pi i's at least one variable gets restricted, okay, and the total number of ones in all the AIs is how many? S. The total number of variables that are getting restricted is S. Okay. So, each AI has at least one 1 and total number of ones in all the AIs is equal to S. Now, using these two you can find out that the, so I will just leave this as an exercise, that the number of sequences of the above form is at most 2t to the power s. Okay. Also note one more thing, that k is actually less than or equal to s. Okay. So, the number of pi 1 up to pi k, that is at most s, because in each of these there is at least a single one. Okay. So, you can, so this is again a simple combinatorial argument, you can think about this. Okay, so this completes the proof of Hastad switching lemma. Okay. So, the key aspect, I mean, of course, this is a very complex proof, and okay, so one more thing that I should mention here is that the proof that Hastad actually gave, so this proof was given by Hastad during his PhD. Okay, so this was part of his PhD thesis, and the proof that he gave was slightly different. He gave a probabilistic argument. He did not explicitly give the construction of all this, so he argued that such such an injection actually exists. So, this constructive proof was actually given later by Razborov. Okay, so Razborov, so this proof is actually even simpler. So, his proof, Hastad's proof is a little bit more complex, but this was a simpler proof that was given by Razborov. And what else did I want to mention? Yeah, so of course, we in this lecture we only proved it for the constant 16, but as I said that with a little bit more work you can actually prove it for gamma, where gamma equals 4.16. And also the other thing is also true, even if you prove it for 16, you can also prove the size lower bound with the constant 16 as well. Okay, you can actually modify the proof that was given last time so that it works with the constant 16 as well. So, both ways are actually open. Okay, okay, so I will stop here. Yeah, yeah. So, that as I said, it actually comes from solving an equation. So, you get a equation using this, I mean, so basically they showed that this is bounded by some alpha to the power s, and that alpha is basically an equation which has this TP TPNN, and then they showed that solving that equation you get it as gamma, you get alpha as equal to gamma PT. So, gamma PT is one of the roots of that equation. It is a, yeah, so it is a, I mean it is not a linear equation, I do not remember. It's an exponential equation, yeah, yeah. See, there are actually many places where we can improvise a little bit, right, because if you remember last time the probability p that we took was how much? It was n to the power minus 1 over d minus 1, right, and we just said that well that is less than half for d greater than or equal to 3, but if n increases actually that becomes much lesser than half, and here we are only showing it for n for p less than half. That is one place where you can improvise for large n of n, right. And the way, yeah, what else? Yeah, I think the way we did that counting, I think I have erased it, but so where we had this 2 factorials, okay, and we took that ratio of 1 factorial over another, and we took the maximum term of the top factorial over the minimum term raised to the power s. I think that can also be improvised. So, yeah, yeah, so I do not know much how that thing works, but of course it can be made smaller. But the important thing is that the essential idea is this construction of this injection. Okay, so construction of this 1-to-1 map, and yeah, so this is the crux of the proof. It is, yeah, yeah, it is a general function. It is a general function. No, it is not, well, it is not a general function actually. It is a function which is representable as a TCNF. Now, any function, as I said yesterday, that day before yesterday, that any function can be represented in CNF form or DNF form, right. But for small t's, it is not necessary that every function will be representable. If you take t to be large enough, of course, if I take t to be n, then any function is representable as NCNF or a NDNF, right. So,
But if I take the t to be large, then p has to be taken very small.
yeah.